Hey everybody, today we're doing more with hypothesis testing of proportions. We're going to do a full example from start to finish, and then we're going to talk briefly about hypothesis testing of proportions from the binomial perspective. Let's go. So here's the example we're going to be working with today. A large university advertises that 65% of its students graduate in 4 years or less. I worry that they're overestimating it, so I collect a simple random sample. I talk to 120 people. I find that 68 of them graduated on time in that time frame. Is there sufficient evidence to reject the university's claim? 68 out of 120 is about 57%, so obviously less than 65%. However, that could just be due to random chance. Just how unlucky would I have had to have been to get a sample like that? That's what the p-value is going to represent. If the p-value comes out to be less than 0.05, alpha equals 0.05, then we're going to reject the null hypothesis, reject the idea that the actual proportion of students that graduate in 4 years or less is 65%, and instead accept the idea that it is less than that. So as always, we start with hypotheses. H naught, the null hypothesis, is the idea that our results are just due to chance, that the graduation rate in 4 years or less is actually 65%, and I got 57% just through luck of the draw. The alternative hypothesis is the thing that we're interested in establishing, so p less than 0.65. As always, notice that these hypotheses are written in terms of parameter values, numbers that are describing a population. The sample data, the 68 out of 120, is what we'll use to decide between these two. The hypotheses are never formulated in terms of samples. A one-sided test is appropriate here. We don't particularly care if the university underestimates its 4-year graduation rate. We started off by saying we are worried that they have overestimated. So as always with hypothesis testing, we assume our null hypothesis. We assume that the parameter is p equals 0.65. And we compute the probability of getting sample data like ours just by random chance. The probability of getting a p hat less than or equal to 68 out of 120. So notice that I've written that probability statement like that because we have a one-sided hypothesis test here. We're specifically interested in the probability of getting a low p hat given the parameter p. So by the central limit theorem, p hat is approximately normal. It's going to have a mean, which is going to be the same as the population proportion, and a standard deviation that's closely related. The standard deviation of p hat is going to be the square root of p times 1 minus p over n. Again, it's this idea that if we were to get this sample of size 120 over and over and over again, we'd get different p hats every time, that there's going to be a distribution to that with a center and a spread. Here we're just quantifying what that center and spread would be. Great, so now that I know the sampling distribution of p hat, I can find the z-score of my particular p hat. Here p hat is 68 out of 120. So I do what I got minus what I expected divided by the standard deviation, again, using the mean and standard deviation of p hat. So it's p hat minus mu sub p hat over sigma sub p hat. And I got negative 1.91. To get the probability that p hat is less than or equal to 68 out of 120 just by random chance, I'm thinking in terms of a normal CDF. And I've got a picture of that here. I need the probability of getting a z-value less than negative 1.91 just by random chance. And that's going to be my p-value. So in R, that's p-norm of negative 1.91. You can also do that with one of the many applets that are available online, of course. Here it comes out to be 0.028. That p-value of 0.028 is less than the alpha that we set of 0.05, and therefore we reject the null hypothesis and conclude that the university has indeed overestimated their 4-year graduation rate. Now, of course, we recognize there is a possibility that we're wrong about that. Specifically, there's a 2.8% chance that there's a type 1 error. That p-value of 0.028 specifically represents the probability of getting a result this extreme or more extreme just by random chance. That's specifically when we have that type 1 error, a false positive. Okay, a few words about the binomial distribution. The whole game here in doing the significance test was to evaluate the probability of getting a p hat less than or equal to 68 out of 120 just by random chance. And we did that in the previous slides using a normal approximation. Historically, that was by far the easiest thing to do. There were normal tables, and you could just look them up. In contrast, evaluating this directly using the binomial distribution was computationally prohibitive. Nowadays, of course, that's not the case, and we can evaluate the probability of getting a p hat less than or equal to 68 out of 120 very directly. We're looking at the binomial distribution b of 120, comma, 0.65, 0.65 chance of success, n equals 120. Probability of getting no more than 68 successes. So the middle line there is just specifically applying the PMF for the binomial distribution. And I did that using technology. For this one, I used R, but you can also do it directly in Wolfram Alpha. And I got 0.036. So we still would have rejected the null hypothesis using this p-value. Notice that it's a little bit different. Maybe it's surprising how different than it is from the one that we got using the normal approximation. It's off by 0.8% of a percentage point. So why isn't it closer? Well, if you think way back when we did the half-unit correction, continuity correction for the normal approximation to the binomial distribution, we saw errors like that. If we really wanted to get that normal approximation to be exceptionally strong, we would want to apply that. But at that point, we're doing more work for an approximation, and the whole point of the normal approximation was to do less work. So you kind of make a decision on these problems whether you want something exact or approximated. Of course, the normal approximation gets better when n gets larger, and so 120 is not tiny, but it's not huge either. So you want a larger sample size, of course, here.